Good afternoon, everyone. We're going to go ahead and start into a new unit. This is going to be taken from chapter 13 in your textbook on chemical equilibrium. And let's go ahead and dive right in. Our learning goal, you're going to start seeing these a little bit more often, but our goal always is that you'll be able to reach that score 3.0. Now, without using notes, student will be able to apply the basic principles of equilibrium and, to chemical reactions and how it applies to kinetics, and understand a little bit of how it applies to kinetics. Now, I want you to go ahead and rate yourself at this point. Where are you? Now, most of you have no idea what chemical equilibrium is, so that's completely understandable. Now, let's go ahead and get started. Now, equilibrium itself is a state where all the reactants and products remain constant with time. Now, notice that I didn't say that it's the point at which all of the concentrations are equal. No, we're just looking at where the rate or the concentrations actually remain the same over a certain period of time. So we're going to look at the example here. Consider we have dinitrogen tetroxide gas. Now, when it's placed in a closed container that's been turned into a vacuum, we've gotten all the other gas out at 100 degrees Celsius, then we're going to start to see nitrogen dioxide form. Now, there's a reddish brown gas, and it actually is formed by decomposing the dinitrogen tetroxide. This is the normal reaction that we're used to seeing, and this is called what we call the forward reaction. Okay, now as that reaction goes, this is the only thing that's usually happening. However, as more of the NO2 or the nitrogen dioxide molecules form, they can get to a point where they actually start to react with each other and produce dinitrogen tetroxide. This is what we call the reverse reaction. So we started off with the reaction going one way, breaking down the dinitrogen tetroxide to form the nitrogen dioxide. But over time, we actually start to break that back down and reform our dinitrogen tetroxide. Now, it says as the concentration of dinitrogen tetroxide increases, or N2O4 increases, the forward reaction slows down. So it's breaking down, and then forward reaction is going to start to slow down. Conversely, as the concentration of NO2 increases, the rate of the reverse reaction increases. At the same point, or at some point, sorry, the rates of the forward and reverse reactions are going to be equal. They're going to be breaking down as fast as they're being formed. Then we say that the reaction has reached equilibrium. Now, this is going to be represented by the double arrow. So if ever you look at a reaction, you see the double arrow that looks like this, or one that looks somewhat like this, I'll try to do my best, you know that it's an equilibrium step or an equilibrium reaction that's taking place. Now, when we look at this graphically, we're going to look at it in terms of two different things. If you look on the left, you're seeing that this is the concentration versus time. Just as we saw before with our kinetics, we see that the NO2 is increasing, and then it gets to a point where it levels out. Whereas the N2O4 decreases, it levels out. This one never reaches 0, nor does the NO2 ever reach 100%. Now, if we look at the same thing in terms of rate versus time, coming to a point where they both equal out, and again, that's called our equilibrium. Okay? Now, when we reach equilibrium, we're going to say that it's macroscopically static, or appears to have stopped. When we look at the reaction, it will look like nothing's really happening. Everything just seems as though it's come to a halt. But microscopically, it's going to be dynamic, or it's constantly moving and changing. It's going to be adjusting and getting to that point of equilibrium. The same thing is happening here with this reaction with the Born-Haber process. You see that our amount of hydrogen gas versus our nitrogen gas, they're decreasing, and they hit a certain point where all of a sudden it levels out. Same with our ammonia. This is another reversible reaction that we're actually going to study and do some examples with in class. But the key is, again, not that the concentrations will be the same, but the rate will be the same with time. Now, just as a little bit of an introduction, if I were to place this reaction going on in a closed vessel. There's going to be a slight shift or a point where the reaction tries to adjust itself to get to that equilibrium. So we have H2O plus carbon monoxide is going to yield hydrogen gas and carbon dioxide. If I were to add more water in the form of a gas to the flask, how do you think the concentration of each chemical is going to compare to the original concentration after the equilibrium is established? Taking a look at what's going on, if the reaction was going and it finally reached that equilibrium point and I added more water, what do you think is going to happen overall? Well, to give you an idea, because of the fact that it was at equilibrium and everything was fine until I added more water, this is actually going to cause the reaction to shift in this direction. Notice also that as we go through this, I'm not going to say so much going to products. We may say the right side of the equation versus left side, or shift left or shift right. It's just saying what's going to happen or which direction the reaction is going to move. Now, to reestablish the equilibrium, since I added more water, that means I'm going to have to push the reaction to form more of our products on the right side of our equation. Now, giving you the same opportunity, take a look what's going on here. Same reaction, but now we've gotten back to equilibrium, and now I add more hydrogen gas to the flask. What do you think is going to happen to the concentrations of each of them after the equilibrium is established? Which way is the reaction going to shift? And try to have an idea of why you think that's going to be what would cause it. Now, this is the end of part one. You notice that part went kind of quick. Now, I want you to reevaluate where you are. Bring your questions when you come into class, and then we're going to actually look at how we can touch up some of these things and make sure you understand them, so that as we go through this next week, we can start to prepare you for the types of questions you'll get for the AP exam. Have a great evening, and I look forward to seeing you in class.